This program was brought to you by Coller Institute of Venture at Tel Aviv University.
I wanted to give something, maybe it relates to what I will relate to the talks about the university before. It's when we teach, we want to always kind of give the basics, because then in 30 years go know how the world will look like, and what we teach today may be irrelevant. But if you have the good basics, then any graduate you have will be able to pick up the knowledge and continue a lifelong experience of learning, and we'll have the basis that basically our university hopefully give. So let us. So this is the talk. It will be more on the basics, and then we'll jump a bit on some engineering things, and we will kind of present some kind of an interdisciplinary. I came from a technical university, and in a technical university, everybody is an engineer, or the most. And what is wonderful in coming to a university that is so broad that you can just sit to lunch with the head of the Earth Sciences Department, Professor Shmulik Marko, and discuss about ports in the first century, or getting this knowledge. So I will take a bit of this, and hopefully we'll have time to show everything here. So let's start with a movie that kind of will maybe show us a bit. It's a movie made by NASA, actually, not to my request, but fitting exactly. So this is, what does it show? It shows basically how the field, the ocean, is so in perpetual motion, basically. Everything changes. So if you're sitting here today and you close your eyes and you open them, you find out yourself a few seconds afterwards in the same place, or a few minutes. But in the ocean, if you put something in the ocean, close your eyes, open it again, it will be a completely different place. And I think this is what this kind of movie tries to show, the entrance and the straits, and what marvelous motion. I can sit and look at this like for hours. It's mesmerizing. So basically, what do we want to say? Sorry to cut it. I can send you the link afterwards. But we don't have that much time. So what do we want to say? That actually currents, it's a fluid environment. Everything moves, So whatever you use, we thought we used the ocean, we just dump things and they just fly away, and that's it, they disappear. We have a little black hole, and we just pump the sewage there and throw things and plastic and whatever. But it's not that simple, and people will afterwards, Marcos will give a talk about models, and you will see more this direction, how we attend this. But how do we look at this? How basic people in fluid dynamics look at the motion? So you have the Eulerian approach and the Lagrangian approach. And the Eulerian approach is basically something, you have a control volume, and then you say, okay, we have some kind of a control volume, this thing, we close our eyes, we look, we open again, after some time, we look at the same control volume. The water there is not the same water, but we look what happens there. If you put some kind of a little propeller and measure the wind, that's this concept. It's an Eulerian concept. A Lagrangian concept says, okay, let's take a material volume, then we close our eyes, open it after a few seconds. The water that was here actually deformed and came to a different place. And these are two conceptually different ways on looking on fluid flow. So what are the measurements that we use? Ones are Eulerian, So you have a mooring system and you measure something. You have a buoy, you measure the wave. You have satellites that go above and measure oceanographic, let's say, sea surface temperature. You have models that afterward will be talked about more in detail that are Eulerian approach. They look at an area, the water can flow through there, but they give the velocities in each location. Here's a system that we plan to put in Israel, actually already funded by the Ministry of Science and Israel Science Foundation, and also with the great support of Tel Aviv University and my faculty, School of Engineering, Faculty of Engineering. So this is HF radars that we plan to put and cover the whole region of Israel. And when I came to Tel Aviv University, the say was, we look at the sea. We look forward to sea. I think it's something that connects between Portugal and Israel now, that with the economic value that we found out that in our case, the gas findings near the shores of Israel, and in Portugal case, the expansion to the economical zone and expanding it and understanding this value, it's very important to understand how this environment, how it moves. Maybe we talk a bit about this later, but let's jump to the Lagrangian ones. The Lagrangian ones are things you throw in the water. Yeah? So look here, in 1990, there was a container falling. The container in front of the US, the container just contained sneaker shoes, yeah? Nike sneaker shoes. So the Oceanographic Institute, Scripps Institute, that is here in San Diego, a bit down, above Baja California. So they say, okay, everyone that brings me a shoe, yeah, will get a new Nike shoe. Yeah? As long as you date where you found it and when. Yeah? And then they kind of track these Lagrangian tracers to where it fell in. And you see this dispersion of shoes all along the coast of the US. So this is a Lagrangian observation. You have drifters, you have floaters. I saw that somebody will maybe talk a bit more on this. All kind of floaters that float around the ocean, sink, measure, go up, transmit to satellites, etc. And then you can get a general circulation model. But this is the large scale, how the currents drive in general, yeah, like the climate. Yeah, this is the winter, the summer outside. But then there are smaller and smaller scale, from the large scale that are in the 18th century, kind of more or less understood. You go to mesoscale, like it's smaller scales. They are defined by a Rossby number. It's kind of a measure on how the effect of Earth's rotation is affecting them. Then submesoscale is something that we still need to research, and to the smallest scales, like meters, centimeters, and millimeters, like turbulence measurements or waves, yeah, that are in the smaller scale. So you have this going down, but actually people in the Earth Simulator Center in Japan, it's a big computer farm that they are simulating the ocean and the flow. Huge, they understood that actually you need a small scale also to drive the upper scale. So it's, everything is connected, so you need to understand what's going on here. The second thing is, let's move to the ocean waves to give some basics of what it is, yeah? So ocean waves, maybe the local people kind of recognize this place, yeah? This is the world record. I think it was broke again in the same place not that long ago, a week or two. This was Mekanmara, 100 feet, like 30-something meter wave. You don't want to put a wave buoy there to take the waves. Yeah, it won't survive this thing, but somehow crazy people do. It's fascinating. Actually, it's great. If you go under such a wave, much smaller wave, you will feel like you are in a laundry machine. Yeah, it's it's a bit crazy, the suction. So what engineers do with this? Yeah, they need to protect from these waves. Yeah, you see like the lighthouse, and this is a dike protection of water. See how the overtopping, the wave that just crash on this dike, they are above the lighthouse. Yeah, it's huge. You have land reclamation and you have dikes protecting. That's what happens when a dike fails and the water rushes into the shore. You want to build artificial islands, for sure, for a place small as Israel, with neighbors that want, let's say, want us to expand there. We look at the sea, yeah. We look at the sea and we say, okay, this is a lot of land, very peaceful, or at least predictably peaceful. And we want to maybe build there an airport or facilities, yeah, an airport that doesn't make noise to the people that live nearby and can operate 24 hours a day. Yeah, it's like, think of an airport, you put billions and then you shut it out for 25% of the day. Yeah, it's 25% less income. No, it's a problem. So we don't talk about money. We are scientists, so we leave the scientific the calculation to others. We just show the vision. Of course, wave energy offshore was very impressive talk, the one before us. Offshore energy, we need to understand how the flow, how the waves is behaving. So what are waves, actually? What are waves? Yeah. Waves, let's see if you are for Porto or for, yeah, you like football. And basically, you see the people are making a wave in the stadium. Are the people moving to where the wave propagates? They're not. They're still by their seat. Yeah, but the wave propagates. So what happens here? It's actually some kind of a disturbance that propagates, but the people don't move much. They just go up and down in their seat. So the propagation of wave, bless you, is actually a propagation of a disturbance. The same in sound. Actually, the molecules, when we talk, are just moving back and forth, yeah, from our sound cords. But the molecule of air don't get to you. The sound gets to you when I'm talking, but not the molecules of air. It's not a flow. It's something else. It's a disturbance that moves. Some basic properties. I won't. I'm doing a lot of math, but I won't. I won't put it to you. But there is a wavelength between peak to peak. That's a simple sinusoidal, the most simple concept of a wave. Peak to peak, and there is a time. If we stand here and we time up until when the next peak comes, this will be the wave period. The wave celerity will be just this length divided by this time. We call something frequency or angular frequency. It's 1 divided by this time, or 2 pi divided by this time. A wave number is 1 divided by the length, or 2 pi divided by the length. So these are the basic building blocks that we talk about. What happens under a wave? A deep water wave, ones that is not affected by the bottom. What is deep and what is shallow, actually, everything is relative, like Einstein said. It depends on the wavelength. Yeah, if it's deeper, like this, if it's deeper than half the wavelength, this will be deep. If it's if it's not, so it will be intermediate or shallow water. So actually, for a 100-meter depth, 100-meter wave, 50 meter and more will be deep. For 200, this will be shallow. Yeah. So the depth itself, the number is related to what wave we are talking about. So this is the circular thing. This is the washing machine effect. When you are diving under a wave, what you feel. And in a shallower, you will have a more elliptical kind of behavior. So this is the basics about this. Fish farming, just courtesy of Professor Nitai Dreamer, my colleague that designed this system. It's survivability. People a few years ago didn't think you can make fish farms in the open sea. Yeah, and now they always put it in protected areas, but the environmental cost is huge because fish shit, yeah, sorry. And it's a lot, a lot of fish, so a lot of the other word. And then you don't want it in a closed basin. Yeah, if you dive by something like this, this is not fun. you dive. We had this in Eilat, and you dive by it, and it's not fun. And then they actually kick them out of Eilat because this is bad for the coral reefs and stuff like this. So they needed to go to the open sea, and actually this system, in order to survive, is actually acting like a submarine. It's basically, you see it like that, and it basically dives down when there are waves, and that's actually what the fish do. When there are strong storms, they dive down, because if we look at this, you see it just decays, the movement of the wave, so it dives down. That's why submarine people, if they go on a ship, they can feel seasick because they just dive down when there are waves. So fish farming. So we didn't think about it. Think how much people there will be. Think how much sea space you have. You can grow seaweed farming. There is so much potential in the sea. Sorry, not much equation, but I will talk about this a bit. Dispersion. Ignore equation. Dispersion and non-dispersive waves. What are waves? Yeah. Basically, sound waves, you know what was the sound speed of waves, 330 meters per second. You can time. There is like the thunder, and then there is the lightning. You time between the lightning and the thunder. You know how long it is. You count the seconds. You know how far the thunder was, because you know the speed of sound. What is the speed of waves? Why nobody told us what is the speed of waves? We know the speed of light, the speed of sound. What is the speed of waves? So speed of waves is changing according to what wavelength or what frequency you are talking about. So this is a dispersive phenomenon. That means that if I speak to you in sea waves instead of sound waves, so the first line will hear what I'm saying exactly as it is. The second line, it will be, the wave will disperse. The long wave will arrive faster than the short wave. And as we go back and back and back, the longer waves will arrive first. So if I say something, here, and we understand, and the back rows will hear something like, whoa. We'll hear first the basses, the long wave, and then the short waves, the high pitch, the frequency. So that's a totally different phenomenon. Let's jump a bit how it behaves. What happens because of this? In shallow water, actually, these waves behave more or less the same as sound waves, and their speed depends on the depth solely, and that's why waves grow in the near shore, because their speed becomes slower, so they need to transfer the same energy, so become stronger or higher. And we have all kind of phenomena of this. Let's see just how wind waves are created. Some temporal evolution. This is the lab of Professor Schemer in our department, and amazing lab. It's all robotic. You can put it and now do statistics for, I don't know, the whole night without the student standing and putting it on. And so you can do really ensemble averaging and crazy stuff. So that's how the wind start blowing and the waves start growing. And this is ensemble average on thousands and thousands of realization. Because if you measure the wind, this is the wind measurement down here, this will be looking like that. But when you have a robotic channel like this, you can average and see what's the average and find good statistics for this. Let's jump. Sandy shore, dynamic balance. Just a bit, we see Hurricane Bonnie, a hotel. Hurricane Bonnie approaches. I don't know if it doesn't show. So Hurricane Bonnie approaches and actually eats this part of the sand. Yeah. So the shores are actually in a dynamic balance. We think it's constant, but it's actually not. Yeah. So yeah, here it is. You see it is cut. And after Hurricane Bonnie, they put here protections. Protection in order to protect the sea. So what happens if you don't design this well? Do you recognize what it is in the picture? It's actually a port, a small fishing port in Taiwan. And the mayor just decided to extend this breakwater because it wasn't calm. And he extended the breakwater, and the nice beach here just got into the port. So, so this is the extreme case. He dredged it, actually. Dredged, took it out, put it back. There was a nice beach for 2 more years, and then the beach came back. So you don't want to fight nature. You want to design it well as an engineer together with nature. So this is the story of Caesarea. Caesarea is a wonderful place in Israel. It's actually a national park. It has a amphitheater and hippodrome, like horse racing and all kinds. It's a very, very beautiful place. It had a big port. Actually, it had 2 parts of the ports. One is here, and here from the aerial view, you can see this is what was underwater. This was the port's closure, and that's how it looked in all time. Actually, they had the same problem, that sand got in, yeah? But they didn't have machines and dredgers and to take this sand out. They had people with sacks. You can't take a lot of sand like this. So they were very ingenious in using and knowing the environment and using it for this. Actually, this port was active for 1,300 years, and it wasn't devastated by storms, yeah? Devastated by Salah ad-Din kicking out the Crusaders, yeah? And because Crusaders used this in order to bring troops. So actually, he ruined this in order for them not to be able to come back, yeah? So this was it. So this is bigger than what it seems here. It's kind of closing. And he had the same problem, actually. And so one thing he did, actually, is doing here some kind of channels. Yeah? Channels that the waves penetrate and bring water inside. And then if they bring water inside, when only the waves that crush above these channels, and you can close and open them, and this water that comes inside flushes a bit the port system out. So flushes the sand that gets in out away from the port. So that's very ingenious. Yeah, actually, you use the water. Okay, so we just close it. We are dead in time almost. So this is just recently known. Dre 2012. They are found. They always knew they have all kind of dams here, a bit north. Caesarea is a bit here, where Herod's port is, and this was all flooded. and then they didn't know what was done. And actually, if you look at this, you have here two aqueducts. They look like this, the higher aqueduct and the lower aqueduct that looks like a cave. And the higher aqueduct was water, and the lower one we didn't know exactly. People thought maybe it's water, maybe it's not. But actually, what it is, it's a flushing system to clean the port. It's one of the biggest flushing systems in the world. It was used these are the dam opening, and it went to the port, and basically it was a big toilet. So you had here the Niagara filled with water, high potential. This is like the thing, it opens, it opens this dam, and then it just flushes in this pipe, through the pipe to the port, and cleans the port. So basically that's in a short story how people in old time, and it's a thank for the Shmulik Marko's Earth Science School in our department that we talked about this, that kind of, I got into this understanding. Yeah, it's very interesting research that he does. But okay, closing remarks. Sorry. This is a picture I took yesterday in visiting an Oceanographic Institute here in Lisbon. Actually, Professor Abreu was visiting us, I think, a month ago, and we actually worked on the same stuff in his PhD, and it's very interesting. Actually, the advantage, so I don't want to disencourage you in investing in the sea. On the contrary, I want to say the sea is a complicated place, and that kind of prevented us from getting much deeper in. But now governments are putting a lot of funds in order to understand what's going on there, in order to measure the bathymetry, in order to calculate the waves, to make models, to measure like with these radar systems. So actually, this is the time to get in, because there is so much governmental fund that will give the information if you only find your own thing to exploit out of this and say, okay, we can make this, commercialize this part. Now it's the time to do it. Okay, so I thank you much for listening.
This program was brought to you by Coller Institute of Venture at Tel Aviv University.